Welcome to your introduction to electricity. Electricity is the movement of electrons. It's an invisible force that provides light, heat, sound, and motion. When we're looking at electricity at the atomic level, these are the simplest form of matter, which are elements. Atoms are the smallest piece of an element containing all of the properties of that element. Electricity at the atomic level. These are the components of an atom. The nucleus is the center portion of the atom containing the protons and neutrons. Protons are positively charged atomic particles. Neutrons are uncharged atomic particles. The atomic number is equal to the number of protons in the nucleus of an atom. The atomic number identifies the element. How many protons are in this nucleus? Electrons are negatively charged particles. Electron orbitals. These are orbits in which electrons move around the nucleus of an atom. So here we have orbits, and we have electrons on the orbits, as indicated by these little green dots. Valence electrons are electrons on the outermost ring of an atom. So how many valence electrons are in this atom? 2. 1, 2. Models and representations of atoms. How do we understand and describe what we can't see? Over hundreds of years, scientists have generated mathematical models to describe the structure of atoms, how particles interact, and how the structures of atoms give them their physical properties. This is the Bohr model. It shows negatively charged particles orbiting around a nucleus. Another type of model is called the electron cloud model. Probability function describes a region where an electron is likely to be found. And in quantum mechanics, we have this chart. It is a mathematically described interaction at a nanoscale level of the representation of atoms. As you study in more depth, you'll learn that the periodic table reflects electron configurations of elements based on our understanding of all these models of the atom. These electron configurations and consequent location on the periodic table identify an element's properties. Here we have a table, and we're going to talk about the maximum number of electrons per orbit. So orbits closest to the nucleus fill up first. So here we have the nucleus, and here we have an orbit with 2 electrons. So the orbit number here is orbit number 1, and it has 2 electrons on it. This particular atom that we're showing is going to have 7 orbits. In orbit number 2, there's 8, and so this is showing the maximum number of electrons per atom. The valence orbit is the outermost ring, and this one has 8. So the max number of electrons is equal to 2n squared. N equals the orbit number. Let's look at copper. So on a periodic table, copper would look like this square with this information. You have Cu, the abbreviation, the name, and then 29. So electricity at the atomic level. Electron orbits. Atoms like to have their valence ring either filled up with 8 or empty with 0. So how many electrons are in this valence orbit? 1. So this is copper. Is copper a conductor or an insulator? It's a conductor. We'll find out why in a few moments. Here we have sulfur. This is the atom for sulfur. How many electrons are in the valence orbit for sulfur? 6. Is sulfur a conductor or an insulator? It's an insulator. And again, we'll find out why in just a few moments. An electron from one orbit can knock out an electron from another orbit. Boop. Just like that. When an atom loses an electron, it seeks another to fill the vacancy. Electricity is created as electrons collide and transfer from one atom to another atom. So here we have electron. That electron just moved through these atoms very quickly, knocking out the other electron. Play it again. Bam, bam, bam. So that's how electricity is created. Electrons colliding and transferring from atom to atom. Let's talk about conductors and insulators. In a conductor, electrons flow easily between atoms. In an insulator, electron flow is difficult between atoms. A conductor has 1 to 3 valence electrons in its outer orbit, while an insulator has 5 to 8 valence electrons in its outer orbit. So an example of a conductor would be silver, copper, gold, and aluminum. Examples of insulators would be mica, glass, and quartz. Let's identify conductors and insulators using this image. So here we have some pliers and we have wire. So which is the conductor and which is the insulator? Conductors, that would be the conductor because it's made out of type of metal. Same with the wire. So we want electricity to flow easily through these. The insulators would be the rubber parts of these components. You don't want electricity flowing through the handle of something. You might get shocked or even worse, electrocuted. And an electrical circuit is a system of conductors and components forming a complete path for current to travel. So in a circuit you have voltage, current, and resistance. Voltage, otherwise known as volts, is symbol represented by a V. Amps is A, and ohms you have the omega symbol. Let's talk about current. Current is the flow of electric charge. It's measured in amps, amperes. So here we have to imagine a tank of water. So this tank in this example is going to represent a battery, and we have a pipe going out to a faucet. So imagine the water is your electricity. So your tank, your battery is full of water. The electricity is flowing from the battery or the tank through the pipe, and it's going out a faucet, which is a switch. When the faucet switches off, is there any flow? Is the water going through it? No. When the faucet switches on, is there any flow? Yes. Current in a circuit. When the switch is off, there is no current. When the switch is on, there is a current. Conventional current assumes that current flows out of the positive side of the battery through the circuit and back to the negative side of the battery. This was the convention established when electricity was first discovered, but it's not correct. This is wrong. Electron flow is what actually happens. The electrons flow out of the negative side of the battery through the circuit and back to the positive side of the battery. However, conventional current versus electron current and scientist versus engineer. Since this is an engineering course, guess who wins? Conventional current. So we're going to be looking at circuits using conventional current because it's just simpler in terms of doing all the math and wiring up our circuits. We want to go from positive to negative whenever we are measuring things. So the direction that the current flows does not affect what the current is doing. Thus, it doesn't make any difference which convention is used as long as you're consistent. Both conventional current and electron flow are used. In general, the science disciplines use electron flow, whereas the engineering disciplines use conventional current. Since this is an engineering course, we will use conventional current. Voltage is the force that causes current to flow. It's measured in volts, or V. Again, same example, same imagery. So let's imagine a tank, which is the battery, and water is the electricity flowing through the pipe. When the faucet is off, is there any pressure? Yes, pressure is pushing against the pipe, tank, and the faucet. When the faucet switch is on, is there any pressure? Yes, pressure pushes flow through the system. So voltage in the circuit. When the switch is on, the battery provides voltages that will push current through the bulb when the switch is on. Resistance is the opposition of current flow, measured in ohms, symbolized by the omega. All materials have resistance. Conductors have little resistance. Insulators provide a lot of resistance. Some electron components, such as resistors, have specific resistance. These are often needed to reduce current in order to protect other components or to adjust the amount of current that goes to other components. So what happens to the flow if a rock gets lodged in the pipe? So here we have rock, and it's getting lodged in this pipe. The flow decreases because there's something in the way. So resistance in a circuit. Resistors are components that create resistance. If we put a resistor in this circuit, we reduce the current, which causes the bulb to become more dim. In order to measure voltage, we use a multimeter. So we set the multimeter to the proper V range, as shown here. The positive and negative signs represent polarity and flow. A digital multimeter will give a negative reading if the positive and negative terminals are reversed. The voltage reading can be different between any measured component. You would measure a crossing component to get the voltage. So you would use the leads of the multimeter across the negative and the positive to get a reading. Just like this, you would measure across a component. So a multimeter is an instrument used to measure the properties of a circuit, including volts, amps, and ohms. When you're measuring current, you would set the multimeter to the proper amp range. So you would set it on the amp or the ADC side. Circuit flow must go through the meter in order to measure current. So you'd have to put the multimeter in series with the current, or with the circuit. So you'd have to unattach any leads or wires connected from component through the red to the black. When you're measuring resistance, you set the multimeter to the proper ohms range. You'll see it on the multimeter switch panel. And you would measure across the component being tested. The power must be off or removed from the circuit. So you have to turn the battery off or turn the switch off. Or take the battery completely out. And you would measure across the component to get the resistance. Ohm's law. Current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. The mathematical relationship between current, voltage, and resistance. If you know two of the three quantities, you can solve for the third. Here are the common abbreviations used for voltage, current, and resistance. So voltage is V, or volts, and the symbol is V. Current is I, amps, and the symbol is A. Resistance R, ohms, and the symbol is omega. So V equals IR. So voltage is equal to I times R. So current times resistance. Current is equal to V divided by R. So current, I, is voltage divided by resistance. And resistance is equal to V divided by I. So resistance is equal to voltage divided by current. Here's a fun chart to help you when you are converting your quantities. So we're going to cover the quantity that is unknown in order to find it. So we need to solve for V. You would cover V. That means that I times R equals V. So V equals I times R. If we need to solve for I, we cover the I. And we would divide. So V divided by R equals I. I equals V divided by R. And if we needed to solve for R, cover the R, and you get V divided by I. So R equals V divided by I. Here's an example. The flashlight shown uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? Quickly draw a schematic diagram where you have the battery on this side showing 6 volts, and you have your resistor on this side with the resistor symbol showing 150 ohms. So you're looking for resistance. So you have V divided by R. Well, yeah, you're looking for So you're looking for current, so that will be I. So I equals V over R. So that's 6 divided by 150, which equals 0.04 amps. And we would move the decimal over 2 to get 40 milliamps. Circuit configuration. Components in a circuit can be connected in one of two ways: series circuits and parallel circuits. In a series circuit, components are connected end to end, shown in this diagram. There's only a single path for current to flow. In a parallel circuit, both ends of the components are connected together. There are multiple paths for current to flow. So here we have components are represented as these small rectangles. So parallel, you can see that the components are connected end to end. And components are connected together like kind of like a ladder. And in series, they're connected end to end. Here's a law called Kirchhoff's voltage law. The sum of all voltage drops in a series circuit equals the total voltage applied. This is a formula that we can use to find certain information. And Kirchhoff's current law is the total current in a parallel circuit equals the sum of the individual branch currents. So let's look at this series circuit. A series circuit is a circuit that contains only one path for current to flow. If the path is open anywhere in a circuit, current stops flowing to all those components. So if I take out that bulb, it's going to open up the circuit and all the electrons stop flowing because there's nowhere for them to go. It's just an open space there. Some characteristics of a series circuit are the current flowing through every series component is equal. The total resistance is equal to the sum of all of the resistances. So you would just add up all the resistance to get the total resistance. The sum of all voltage drops is equal to the total applied voltage. This is Kirchhoff's voltage law. So to find the total resistance, it would be RT is equal to the resistor 1 plus resistor 2 plus resistor 3 and so on. To find the sum of the voltage drops, so the voltage total would be equal to V1 plus V2 plus V3. So you would find that is how you would get the total. For the series circuit shown below, we're going to use the laws of circuit theory to calculate the following: the total resistance, the current flowing through each component, and the voltage across each component. So we're going to use the results to verify Kirchhoff's voltage law. So we're looking for total resistance. So that's RT is equal to R1 plus R2 plus R3. So here we have resistance total. So these are the values of the resistors shown in this schematic. So R1 is 220, R2 is 470, and R3 is 1.2K. Add those all up. Your total resistance is 1.9K ohms. Current through each component. So we're using, we're going to look at Ohm's law now. So we're looking for current. We know the voltage is 12. And we have the total resistance, which is 1.9K ohm. So the current in this particular series circuit is 6.3 milliamps. Since this is a series circuit, the current total is equal across all the components. So that's 6.3 milliamps. Alright, so let's find voltage across each component. So that would be V equals I times R, Ohm's law. So we know 6.3 from the previous solution times 220 ohms is equal to 1.397 volts for this resistor. So look at these numbers right here. So voltage 1, current 1, resistor 1. See how it says R1? So the voltage across R1 right here is 1.397 volts. R2 is right here, 470 ohms. So you would do I times R, which equals 2.984 volts. And for, oops, go back. For resistor 3, which is 1.2K ohms, you'd use your current from the previous solution, multiply it by the resistance, and you get 7.619 volts. So if you add all those up, so the voltage across each component, you would see that would add up to 12 volts, which is the voltage total. In a parallel circuit, it's a circuit that contains more than one path for current to flow. So if a component is removed, then it is possible for the current to take another path to reach other currents or other components. So here we have a battery in parallel with two light bulbs. So current is flowing through the light bulbs from the battery. I take out a light bulb. This light bulb is going to still work. Okay, I'm going to pause the video at this point in time, and there's going to be a two-parter for your introduction to electricity, and please find that in the description below.